Below in this lecture I'll answer two questions. In the first question we find out the area of this pentagon, pentagon ABCDE, and in the second question we find out the area of this ring shape. So let's start with the first question. What is a pentagon? A pentagon is a flat closed shape with 5 straight sides and 5 interior angles. This is pentagon ABCDE. It has 5 sides, 1, 2, 3, 4, 5, and 5 interior angles, 1, 2, 3, 4, 5. So in the drawing we have pentagon ABCDE. Those two angles are both right angles. This is side AB, this is equal to 1 minus x units in its left. This is side BC, this is equal to 1 unit in its left. This is side CD, this is equal to x units in its left. Side DE equals to 1 unit in its left. And side EA also equals to 1 unit in its left. Again, our task is to find out the area of this pentagon, pentagon ABCDE. So first of all, we join points E and B together by a straight line. We join points E and C together by a straight line. In the next step, we will extend side BA of this pentagon ABCDE by a straight line in such a way that the extended part will be equal to x units in its length. We find this point as point M. Okay, again, AM equals to x units in its left according to our construction. BA is one side of pentagon ABCDE, and therefore it is absolutely a straight line. When I extend a straight line by a straight line, the result BM is also a straight line. So if you focus on the upper side of the straight line BM at point A, here the sum of the areas must be equal to 180 degrees according to all three. All three says that the sum of the areas on one side of the straight line is equal to 180 degrees. So each angle we have at the upper side of the straight line BM at point A, we have this angle that is the right angle, plus this piece angle. In total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this piece angle must be equal to 90 degrees in its sides. In the next step, we join points E and F together by a straight line. By joining points E and M, we create the right triangle EAM. In the next step, we prove that those two right triangles can go into each other according to side angle side rule. That is to say, we prove that the right triangle EAM can go into this right triangle EDC according to side angle side rule. So prove that the right triangle EAM is going to the right triangle, this right triangle EDC. According to side equals side 1. So why those two right triangles can go into each other? Why those two right triangles can go into each other? First of all, those two sides are both equal to x and therefore they are equal to each other. That is to say, side AM or the right triangle AEM is equal to side DC or the right triangle EDC. Again, side AM or the right triangle EAM equals to side DC or the right triangle EDC. They are both equal to x and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So here this is again EAM. In the right triangle, EAM is equal to this angle, it is the full angle EDC, in the right triangle EDC. And again EAM in the right triangle EAM equals to angle EDC in the right triangle EDC, they are both equal to 90 degrees and therefore they are equal to each other. And finally, those two sides are both equal to 1 unit and therefore they are equal to each other. So this is side EA. The right triangle EAM is equal to this side, that is side DE. The right triangle EDC. And again, if you found out that side EA in the right triangle EAM is equal to side DE in the right triangle EDC, they are both equal to 1 and therefore they are equal to each other. So if you prove that those two sides and the angle that is included between those two sides, this angle, in the right triangle EAM are correspondingly equal to those two sides and the angle that is included between those two sides, this is the right angle, in the right triangle EDC. And therefore those two right triangles can go into each other according to side angle side rule. Those two sides and the angle between them in the right triangle EAM correspondingly equal to those two sides and the angle that is between them in the right triangle EDC. And therefore those two right triangles can go into each other according to side angle side rule. So until now I found out that the right triangle EAM congruent, this is the sign of congruent. So this right triangle EDC according to side against side 1. And from the fact that those two right triangles can go into each other, we will derive two things. The first thing that we will derive that they have also the same areas. That is to say, they are the right triangle EAM is equal to this right triangle EDC again. The right triangle EAM is equal to the area of the right triangle EDC because they can go into each other. And the first thing that we derive from the fact that those two right triangles can go into each other, we derive that side EM of the right triangle EAM is equal to side EC of this right triangle EDC. So it down. EM equals to EC. EM equals to EC. EM equals to EC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two right triangles can go into each other, and therefore those two corresponding sides must be also equal to each other in their lengths. That is to say, EM equals to EC. So if you know that the area of this right green triangle EAM is equal to the area of this green right triangle EDC, because they can go into each other. So if we define the size of the area of this right triangle EAM as Z, that is to say the area of this right triangle equals to Z squared in its size, then the area of this right green triangle EDC must be also equal to Z squared in its size because they have the same areas. What is the length of line segment AB or side AB? From the drawing it is very easy to see the side MB. What is the length of side MB? From the drawing it is very easy to see that MB in total equals to MA plus AB. So as now MB equals to MA plus AB. So MB in total equals to MA, that is X, plus AB, that is 1 minus X. So total MB equals to X plus 1 minus X. X minus X is 0, so we have to leave 1. So MB equals to 1 unit in its length. In the next step, we involve that triangle MEB can go into this triangle EBC according to side. And again, we involve that those two triangles can go into each other according to side. So we have to prove that triangle MEB congruent. This is the sign of congruent. So triangle EBC according to side, side, side wall. So what those two triangles can point to each other? First of all, side AB equals to side BC. They are both equal to 1 and therefore they are equal to each other. So I can know side MB entire EMB is equal to side BC entire EDC. Again, side MB entire MEB is equal to side BC entire EBC. They are both equal to 1 and therefore they are equal to each other. In addition, we already found out that EM equals to EB. So side EM entire EMB is equal to side EC entire EBC. EM equals to EC. Side EM entire MEB is equal to side EC entire EBC. And finally, side EB is the common side that belongs to both triangles. So we can find out that EB equals to itself. It's the common side that belongs to both triangles. EB equals to itself. It's the common side that belongs to both triangles. EB equals to itself. So if you prove that all the three sides of this triangle MEB correspond equal to all the three sides of this triangle BAC. Again, all the three sides of triangle MEB correspond equal to all the three sides of this triangle BEC. And therefore, those two triangles can point to each other according to side, side, side wall. So as you know, if you know that triangle MEB went to triangle EBC according to side, side, side wall. And from the fact that they can point to each other, we will derive that they have also the same areas. That is to say, we derive that the area of triangle MEB is equal to the area of triangle EBC. And again, the fact that those two triangles can point to each other, we derive that they have also the same areas. That is to say, we derive that the area of triangle EB is equal to the area of triangle EBC. In the next step, we calculate the area of this triangle MEB. The area of any triangle equals to the base of the triangles times the height over 2. So the area of triangle MEB will be equal to the base ME, to the base MB, times the height AE divided by 2. And again, the area of triangle MEB equals to the base MB times the height AE over 2. MB is 1 times AE. AE is also 1 divided by 2. So So thereafter MEB will be equal to 1 times 1, that is 1, over 2. So in total, if you found out that thereafter MEB is equal to 1 half square root inside. After MEB equals to 1 half square root inside. And from this equation, 1 half equals to thereafter MEB equals to thereafter EBC, we derive that 1 half equals to thereafter EBC also equals to 1 half square root in size. And thereafter MEB also equals to 1 half square root in size. What is the area of the big quadrangle MEBC? Actually, the big quadrangle MEBC consists of those two triangles. And therefore, thereafter MEBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, the area of the big quadrangle MEBC will be equal to the area of triangle MEB plus the area of this triangle EBC. And again, the area of the big quadrangle MEBC must be equal to the sum of the areas of the two components or two shapes that it consists of. That is to say, it must be equal to the area of triangle MEB plus the area of triangle EBC. Quadrangle MEBC consists of those two shapes and not anymore. Therefore, the area of quadrangle MEBC must be equal to the sum of the areas of the two shapes that it consists of. So the area of triangle MEB is 1 half plus the area of triangle EBC is also 1 half. 1 half plus 1 half is 1. So in total, we have found out that the area of the big quadrangle MEBC is equal to 1 square root in size. The area of this big quadrangle MEBC is equal to 1 square root in size. But quadrangle MEBC consists of two other shapes. It consists of this right triangle MEA and this quadrangle ABCE. Again, the area of quadrangle MEBC, E and BC must be equal to the sum of the areas of the two components, those two components that it consists of, those two shapes that it consists of. That is to say, the area of the big quadrangle MEBC must be equal to the area of this right triangle EMA plus the area of this quadrangle ABCE. And again, the area of the big quadrangle ABCC must be equal to the sum of the areas of the two shapes that it consists of. It consists of one EMA and on the other ABC. So the area, we already found out that from this long equation, those two sides are equal to each other. Those two sides are equal to each other. That is to say, 1 equals to the area of the right triangle EMA plus the area of quadrilateral ABCE. But we already found out that the area of this green right triangle EMA equals to Z. So we can substitute the area of triangle EMA by Z. And we get that 1 equals to Z plus the area of this quadrilateral ABCE. So in total we found out that Z plus the area of quadrilateral ABCE equals to 1. Our task is to find out the area of this big pentagon ABCDE. So what is the area of the big pentagon ABCDE? Actually, the area of the big pentagon ABCDE must be equal to the sum of the areas of the shapes that it consists of. Pentagon ABCDE consists only those two shapes, and therefore it consists of this green right triangle EDC, and it consists of this one, the other ABC. It consists only those two shapes and not anymore. Therefore, the area of the big pentagon ABCD must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of this green right triangle EDC plus the area of this quadrilateral ABCE. In the end, we found out that the area that we are looking for this question, that is the area of this big pentagon ABCDE, is equal to the sum of the two shapes that it consists of. That is to say, is equal to the area of the green right triangle EDC plus the area of quadrilateral ABCE. According to our definition, the area of this green right triangle EMA equals to Z squared in its size. So we substitute the area of triangle EDC by Z plus the area of quadrilateral ABCE. So in total, we found out that the area of the big pentagon ABCDE is equal to Z plus the area of quadrilateral ABCE. But we already found out that Z plus the area of quadrilateral ABC is equal to 1. Second angle, here that Z plus the diagonal ABC equals to 1. I copy the equation that we only found out here. And from this long equation, we derive that the diagonal ABCD equals to 1 square root in size. And again, there are the big pentagon ABCDE is equal to 1 square root in size. Now this big pentagon ABCD is equal to 1 square root in size. So I finish with the first question. In the next step, I'll present to you the second question of this lecture and solve the second question. In the second question, our task is to find out the area of this green shape. Actually, the green shape is a triangle. It is the green triangle A and B. So we have to find out the area of the green triangle A and B. In the drawing, we have a circle. We know that chord AB is the diameter of this circle. So write it down. This is chord AB. That is the diameter of this circle. In addition, we know that this is centered PQ, that is centered to this circle at point M. Point M is the point of tendency of centered PQ with this circle. In addition, we know that those two angles are both right angles. We know that AP, or line segment AP, equals to 9 units in its length. Line segment PQ equals to 4 units in its length. Again, our task is to find out the area of this green shape that is actually triangle, the green triangle A and B. So first of all, we can implement here rule 7. So repeat click on rule 7. According to rule 7, if you verify an angle subtend on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. This is called AB, that is the diameter of this circle. This is peripheral ACB, that subtend on chord AB, that is the diameter of the circle. And therefore, peripheral ACB, okay, again, this is peripheral ACB, that subtend on the diameter of the circle. And therefore, according to this rule 7, peripheral ACB must be equal to 90 degrees in size. So, according to rule 7, any peripheral that subtend on the diameter of the circle must be equal to 90 degrees in its size. We can implement rule 7 in our drawing. Going for the our drawing, we have peripheral angle A and B. This is peripheral angle A and B that subtend on the diameter of the circle. That is called AB. Therefore, it is equal to 90 degrees in its size, according to rule 7. In the next step, we define this angle, the angle PAM as alpha. So, in the right triangle APM, this angle equals to alpha. This angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees plus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. PQ is a tangent to the circle at point M. PQ is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PQ at point M? If this angle is 90 degrees minus alpha, this is a right angle, plus this PC angle, and this angle BMQ, in total the sum of those three angles must be equal to 180 degrees according to rule 3. So I write it down. If you follow that 90 degrees minus alpha plus 90 degrees plus the third missing angle BMQ, total the sum of those three angles must be equal to 180 degrees according to rule 3. Again, if you follow that the sum of the angles on the upper side of the straight line PQ at point M must be equal to 180 degrees according to rule 3. That is to say, 90 degrees minus alpha plus 90 degrees plus the missing angle BMQ, in total the sum of those three angles must be equal to 180 degrees. So here we have 90 degrees plus 90 degrees, that is 180 degrees. Here also plus the missing angle BMQ minus alpha equals to 180 degrees. We have 180 degrees on both sides of this equation, so 180 degrees will get cancelled. So we cancel 180 degrees. In this side of the equation we left with the missing angle BMQ minus alpha equals to 0. Here we add alpha to this equation. If we get that the missing angle BMQ is equal to alpha degrees in its size. This is the missing angle BMQ. That is equal to alpha degrees in its size. So, in the small right triangle BMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this quadrant angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see from the drawing that those two right triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you found out that all the figures of this big right triangle APM are correspondingly equal to all the figures of this small right triangle BMQ, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle APM is similar, this is the sign of similar, to the small right triangle BMQ according to angle similarity rule. for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of this big right triangle APM over side MQ of this small right triangle BMQ is equal to side PM of the big right triangle APM or side BQ of the small right triangle BMQ. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side BQ of the small right triangle BMQ. AP is 9. Or MQ. MQ is the missing side, so we leave this it is. And it is equal to PM. PM is also the missing side, so we leave it as it is. Over BQ. BQ equals to 4 units in itself, according to what is answered the question. So to that, we should find out that 9 over MQ equals to PM over 4. Here we will cross multiply this equation and we get that 9 times 4 is 36, so 36 equals to MQ times PM, or MQ times PM equals to 36. In the next step, we define the center of this circle. This point is point O. So OA is the radius of the circle that will be defined as R. OB is also the radius of the circle. Is equal to R according to our definition. In the next step, we will join points A, O and M together by straight line. Point M is the point of tendency of tangent PQ with this circle. So point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle is equals to R. The radius OM is equals to R, the radius OM is drawn to point M, that is the point of tendency of tangent PQ with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees inside, and this angle is also equal to 90 degrees. In the next step, we will do a construction. That is to say, from point O, that is the center of this circle, we will go perpendicular on side AP. Again, from point O, we go perpendicular on AP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AP. This point is point L. By doing this construction, we created the big quadrilateral LOMP. Inside this big quadrilateral LOMP, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again, in total must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces again must be equal to 90 degrees in size. So inside quadrilateral LOMP we have 4 right angles, and therefore according to 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we write to this quadrilateral LOMP as a rectangle because it has 4 right angles. In the next step, we will do another construction. That is to say, from point B, we will go perpendicular on the radius OM. Again, from point B, we will go perpendicular on OM. The radius OM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and the radius OM. This point is point S. When doing this construction, we created the small quadrilateral BSMQ. Inside the small quadrilateral BSMQ, we have 1, 2, 3 right angles, and therefore this 4 piece area must be equal to 90 degrees in its size. And therefore, according to rule 5, the small quadrilateral SBQM is a rectangle. Write it down. It's a rectangle because it has 4 right angles. In the next step, we will focus on rectangle, the big rectangle LOMP. We know that the opposite sides of a rectangle are parallel to each other. So in the big rectangle LOMP, side LP must be parallel to the opposite side OM. Again, side LP must be parallel to the opposite side OM in rectangle LOMP. But LP is part of the straight line AP. Again, LP is part of the straight line AP. And you know that if a part of the straight line is parallel to another straight line, then the straight line AP itself must be also parallel to another straight line OM. So we found out that LP is parallel to OM. Okay, now LP is parallel to OM. So in the next step, we copy the two parallel lines AP and OM and the diameter AUB in the new page, and we implement rule 50 in the new drawing. So actually, those are the two power lines AP and OM. AOB is the diameter of the circle that touch the two power lines at points A and O. Those two angles are defined as corresponding angles and they are located between the two power lines AP and OM. AP is parallel to OM. Therefore, they must be equal to each other in their sizes, according to Rule 50. Repeat quickly on Rule 50. According to Rule 50, corresponding angles between parallel lines are equal to each other. In the drawing here, line A, this is parallel to line B. The red line C cuts the two parallel lines at those 2 points. Those angles alpha and beta are defined as corresponding angles and they are located between the parallel lines A and B, therefore they are equal to each other in their sizes. That is to say alpha equals to beta. So I can implement Rule 50 in our drawing. In our drawing we have line 8, this is parallel to line OM, and those two corresponding angles are located between the two parallel lines AP and OM, and therefore they must be equal to each other in their sizes, according to Rule 50. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. So in total, we found out that angle APO equals to beta. Actually, it is angle PAO that is equals to beta. This is angle PAO. Is equal to beta. Likewise, also found out that angle MOB also equals to beta. This is angle MOB, is also equals to beta. So in this ring, I write OSB. This angle equals to beta, this angle equals to 90 degrees, and therefore this perpendicular angle must be equal to 90 degrees minus beta, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So this perpendicular angle must be equal to 90 degrees minus beta. Likewise, in this right triangle ALO, this angle equals to beta, this angle equals to 90 degrees, and therefore this perpendicular angle must be equal to 90 degrees minus beta, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two right triangles can go into each other according to angle side angle rule. This is to say, we prove that the right triangle ALO can go into this right triangle OSB according to angle side angle rule. So, why those two triangles can go into each other? First of all, those two angles, they are both equal to beta and therefore they are equal to each other. So here this is again LAO. The right triangle ALO, and it is equal to this angle, this is a angle SOB. The right triangle OSB. again, you should know that angle LAO divided by ALO is equal to angle SOB divided by OSB. They are both equal to beta and therefore they are equal to each other. In addition, AO and OB, they are both the radius of the circle that is equal to R and therefore they are equal to each other. So here, side AO that is divided by ALO is equal to side OB divided by the right hand side OSB. Side AO in the right hand ALO is equal to side OB in the right hand OSB. They are both the radius of the circle that is equal to R, therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees minus beta and therefore they are equal to each other. So here this is again AOL. In the right hand ALO, it is equal to this angle, that is actually angle OBS. In the right hand OSB. And again, if you remember that angle AOL, the right hand ALO is equal to angle OBS, and the right hand OSB, they are both equal to 90 degrees minus beta, and therefore they are equal to each other. So, you have to prove that those two angles, and the side that is included between those two angles, that is R, this right hand LAO are correspondingly equal to those two angles, and the side that is included between those two angles, that is also in this right hand OSB. Therefore, those two right angles can point to each other according to angle side angle rule. We have those two angles and the side that is included between those two angles. This right angle ALO correspondingly equal to those two angles, and the side that is included between those two angles in this right hand OSB. And therefore those two right angles can point to each other according to angle side angle rule. So if you know, I actually found out that the right triangle ALO can point, this is the side of conjoint, to the right triangle OSB according to angle side angle rule. And so we found that those two right triangles can point to each other. We derive that side ALO of the right triangle ALO is equal to side SB in the right triangle OSB. Side ALO equals to side SB. And O equals to SB. Actually, LO equals to SB according to the rule that corresponding sides can point triangles are equal to each other. Those two triangles can point to each other, and therefore the two corresponding sides, that is to say LO and SB, must be also equal to each other and their lengths. So if you define the length of this side LO as x, then the length of side SB must be also equal to x because they are equal to each other. We have the rule that states that the opposite sides of a rectangle are equal to each other. So in the big rectangle LOMP, side LO must be equal to the opposite side PM. But LO is x, therefore the opposite side PM must be also equal to x units in its length. Likewise, in the small rectangle SBQM, side SB must be equal to the opposite side MQ. But SB equals to x, and therefore the opposite side MQ must be also equal to x units in its length. We already found out that MQ times PM equals to 36. So I don't know if you found out that MQ times PM equals to 36. Okay, again, MQ times PM equals to 36. MQ is x times PM. PM is also x. So MQ times PM is x times x, that is 36. X times x is x squared. So x squared equals to 36. Here we take a lot of the equation. If I get that x equals to the square root of 36, that is 6. X equals to 6 units in its length. X equals to 6. And also x equals to 6. MQ is equal to x is equal to 6 units in its length. In the next step, we'll implement the Badawasto one on this small rectangle BMQ. According to the Badawasto one, in any rectangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT, the Russian for Badawasto one. In this small rectangle BMQ, BM squared, that is the square of the hypotenuse, will be equal to BQ squared plus MQ squared. And again, this one rectangle BMQ according to the Badawasto one. Bm squared equals to BQ squared plus MQ squared. Bm is the missing side, so remember as it is, so it is Bm squared equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, that is 16. Plus MQ squared. MQ is 6, therefore MQ squared is 6 squared, that is 36. So to that, we should all know that Bm squared equals to 16 plus 36. 16 plus 36 is 52. So Bm squared equals to 52. Here we take a look out of this equation. If I get that Bm equals to the square root of 52 units in its length. Then BM equals to the square root of 52 units in its length. Okay. This is side BM. This is side BM. This is equals to the square root of 52 units in its length. In the next step, we implement the Vador one on this big right tile APM. In the big right tile APM, according to the Vador one, AM squared, that is the square of the hypotenuse, equals to AP square plus PM square. And again, the big right tile APM, according to the Vador one, AM squared, that is the square of the hypotenuse, equals to AP square plus PM square. The hypotenuse AM is the missing side, so if this it is, and it is equal to AP square. AP is 9, therefore AP square is 9 squared, that is 81, plus PM square. PM is 6, therefore PM square is 6 squared, that is 36. So in total, we have found out that AM square equals to 81 plus 36, it's actually 117. So AM square equals to 117. Here we take out all to this equation, and finally get that the missing hypotenuse AM is equal to the square root of 117 units in its length. This is side AM, that equals to the square root of 117 units in its length. Our task is to find out the area of this green shape. The green shape is actually the right green triangle A and B. So we have to find out the area of the green right triangle A and B. Actually, we know that the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of this green right triangle A and B will be equal to the base MB times the height AM over 2. Again, the area of the green shape that is equal to the area of the right triangle A and B will be equal to the base MB times the height AM over 2. We already found out that MB equals to the square root of 52 units in its length. Times AM. AM equals to the square root of 117 units in its length. Divided by 2. So in total, if you found out that the right hand AB is equal to the square root of 52 times the square root of 117 over 2. Here's the algebraic identity that says that the square root of A times the square root of B is equal to the square root of A times B. Again, the square root of A times the square root of B equals to the square root of A times B. So according to this algebraic identity, we get that the square root of 52 times the square root of 117 is equal to the square root of 52 times 117 divided by 2. 52 times 117 is 6084. This is the square root of 684 divided by 2. The square root of 684 is 78, so it is 78 over 2. That is 39. So if I hold on that the error differential equals to 39 square roots in its size. So write it down. The error that we're looking for this question, that is the error differential in total is equal to 39 square roots in its size. This differential is equal to 39 square roots in its size. So if we finish the second question, in the next step, I'll start with the lecture. We'll start with the first question, of course. In the first question, our task was to find out the error of this big pentagon ABCD. Again, we have to find out the error of this big pentagon ABCD. So what is a pentagon? A pentagon is a flat closed shape with 5 straight sides and 5 interangles. This is a pentagon ABCD. It has 5 straight sides, 1, 2, 3, 4, 5, and 5 interangles, 1, 2, 3, 4, 5. And again, our task is to find out the error of this big pentagon ABCD, pentagon ABCDE. This is the big pentagon ABCD. So, in the drawing, we have the big pentagon ABCD. Those two angles are both right angles. Side ED equals to 1 unit in step, side DC equals to x unit in step, side BC equals to 1 unit in step, side AB equals to 1/6 units in step, side EA equals to 1 unit in step. So our task is to find out this pentagon ABCD. So first of all, we join point C and B together by straight line. We join point C and C together by straight line. In the next step, we extended side BA in such a way that the extended side AM will be equal to x units in its left. Again, AM equals to x units in its left according to our construction. In the next step, we join points M and E together by straight line. By joining points M and E, we created the right hand line EAM. And the right hand line, this is the right hand line, again, EAM. In the next step, we prove that those two right hand triangles can go into each other according to side and side rule. So, when those two right triangles can go into each other. First of all, those two sides are both equal to 1 and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two sides are both equal to x and therefore they are equal to each other. So if you found out that those two sides and the angle that is included between those two sides, this angle, this right triangle EAM corresponding equal to those two sides and the angle that is included between those two sides, this right triangle is here. Therefore, those two right triangles can go into each other according to side and side rule. So at the end, if you remember that the right triangle EAM can went, this is the side can went to the right triangle EDC according to side and side rule. From the fact that they can go into each other, we derive two things. The first thing is they have also the same areas. Any two triangles that can go into each other, they must have also the same areas. That is to say, the area of the right triangle EM is equal to the area of the right triangle EDC. And the second thing that we derive that those two sides are equal to each other. That is to say, ME equals to EC. ME equals to EC. ME equals to EC according to the order that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding sides must be also equal to each other and their lengths. So EM equals to EC. Because of the fact that the areas of those two triangles are equal, is that if we define the size of this triangle as z, that is to say it is equal to z coincident size, then the size of this triangle EDC must be also equal to z coincident size because they have the same areas. In the next step, we found out the length of side MB total equals to MA plus AB. And again, MB equals to MA plus AB. That is to say, MB equals to MA, that is x, plus AB, that is 1 minus x. So in total, MB equals to x plus 1 minus x. X minus x is 0, so we left only with 1. MB equals to 1 unit in its length. In the next step, we prove that the right triangle MEB can go into this triangle EBC. We prove that those two triangles can go into each other according to side rule. And again, if we prove that the right triangle MEB can go into the right triangle EBC according to side rule. So why those two triangles can go into each other? First of all, we just write the formula that EM equals to EC. Again, EM equals to EC. So side EM, the right triangle EMB is equal to side EC, or side EM of triangle EMB is equal to side EC of triangle EBC. In addition, we have those two sides, that is to say side MB of triangle MEB is equal to side BC of triangle EBC. They are both equal to 1 and therefore they are equal to each other. And finally, side EB is the current side that belongs to both triangles. It's very easy to see that EB belongs to triangle MEB and EB also belongs to triangle EBC. So we can write down that EB equals to itself, it's a common side that belongs to both triangles. So if should prove that all the three sides of this triangle EMB are correspondingly equal to all the three sides of this triangle EBC. And therefore those two triangles can go into each other according to side, side, side 1. And again, if you hold on this triangle MEB can go in, this is the side of can go into triangle EBC according to side, side, side 1. And from the fact that those two triangles can go into each other, we derive that they have also the same areas. This is to say, the area of triangle MEB is equal to the area of triangle EBC because they can go into each other. In the next step, we calculated the area of this triangle MEB. The area of the triangle equals to the base of the triangle times the height over 2. So the area of triangle MEB will be equal to the base MB times the height AE over 2. And again, the area of triangle MEB will be equal to the base MB times the height AE over 2. MB is 1 times AE is also 1. Again, MB is 1, AE is also 1, so it is 1 times 1, that is 1 over 2. So in total, we should find that the area of triangle MEB is equal to 1 half square inch inside. Here, the area of triangle MEB equals to 1 half square inch inside. And from this equation, 1 half equals to the area of triangle MEB equals to the area of triangle EBC. We derive that the area of triangle EBC is also equal to 1 square inch inside. Here, the area of triangle EBC is also equal to 1 square inch inside. What is the area of the big quadrilateral EMBC? Actually, the area of the big quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, the big quadrilateral EMBC consists of those two shapes. Those two shapes are triangle MEB and triangle EBC. And therefore, the area of quadrilateral EMBC must be equal to the area of triangle MEB plus the area of triangle EBC. Again, if you know that the area of the big quadrilateral MEBC must be equal to the sum of the areas of the two shapes that it consists of. It consists only two shapes. It consists of triangle MEB and triangle EBC. So the area of the big quadrilateral MEB must be equal to the area of triangle MEB, this is 1 half, plus the area of triangle EBC, this is also 1 half. 1 half plus 1 half is 1. So in total we found out that the area of the big quadrilateral MEBC is equal to 1 square inch inside. The area of this big quadrilateral MEBC equals to 1 square inch inside. So we can write that the area of the big quadrilateral MEBC is equal to 1 square inch inside. But we can look on the big quadrilateral MEBC in another way, and we find out actually that quadrilateral EMBC consists of two other shapes. That is to say, the big quadrilateral EMBC consists of this green right triangle EMBC, this green triangle EMA, and it consists of this quadrilateral EBC. So it consists of those two shapes and not anything else. So the area of this big quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, the area of the big quadrilateral EMBC must be equal to the area of this right triangle EMB plus the area of this quadrilateral EBC. So again, we should find out that the area of the big quadrilateral MEBC must be equal to the sum of the areas of the two shapes that it consists of. It consists of triangle EMA and also consists of quadrilateral ABC. So in total, the area of the big quadrilateral MEBC must be equal to the area of triangle EMA plus the area of quadrilateral ABC. And from this equation, we learn that 1 equals to the area of triangle EMA plus the area of triangle of quadrilateral ABC. Those two sides are equal to each other. That is to say, 1 equals to the area of the green triangle EMA plus the area of quadrilateral ABC. those two sides are equal to each other. So 1 equals to the area of triangle EMA plus the area of quadrilateral ABC. We already found out that the area of this green triangle EMA is Z. So we can substitute the area of the green triangle EMA by Z and get that 1 equals to Z plus the area of quadrilateral ABCE. And again 1 equals to Z plus the area of quadrilateral ABCE. Okay. Our task is to find out the area of this big pentagon ABCD. So what is the area of the big pentagon ABCD? Actually, the area of the big pentagon ABCD must be equal to the sum of the areas of the shapes that it consists of. On the other, the big pentagon ABCD consists only those two shapes. It consists of this real right triangle EDC, and it also consists of this quadrilateral ABC. And therefore, the area of the big pentagon ABCD must be equal to the area of the green triangle EDC plus the area of this quadrilateral ABC. With again, the area of the big pentagon ABCD must be equal to the sum of the areas of the two shapes it consists of. That is to say, it must be equal to the area of the green right triangle EDC plus the area of quadrilateral ABCE. But we already found out that the area of this green right triangle EDC equals to Z. That's correct in size. So we can substitute the area of triangle EDC by Z and get that the area of the big pentagon ABCD equals to Z plus the area of quadrilateral ABC. But we already found out that Z plus the area of quadrilateral ABC equals to 1. So we can write there that Z plus the area of quadrilateral ABC equals to 1. And from this equation, from this local equation, we derive that the area of pentagon ABCDE is equal to 1 square root in its size. The area of the big pentagon ABCD is equal to 1 square root in its size. This big pentagon ABCD is equal to 1 square root in its size. So we finish with the first question. In the next step, okay, I presented you the second question, and we solved the second question of this lecture, so I'll repeat on the second question that we have already solved. The second question, our task is to find out the area of this green shape. The green shape is actually the green triangle A and B. So we have to find out the area of this green triangle A and B. In the drawing, we have a circle. Chord AB is the diameter of the circle. Those two angles are both right angles. AP equals to 9, BQ equals to 4. PQ is a tangent to the circle at point M. Again, our task is to find out the area of this green shape that is actually the green triangle A and B. So first of all, we can implement rule 7 in our drawing. According to rule 7, any perpendicular that subtends on the diameter of the circle is equal to 90 degrees in its size. Perpendicular A and B subtend on the diameter of the circle, and therefore they must be equal to 90 degrees in its size. Chord AB is the diameter of the circle. So perpendicular A and B subtend on chord AB, this is the diameter of the circle, and therefore it must be equal to 90 degrees in its size. The next step, we find angle PAM. This angle is alpha, so the big right angle APM, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. PQ is a tangent to the circle at point M. Point M is the point of tendency of tangent PQ with this circle. PQ is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to all three. All three states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PQ at point M? We have this angle that is 90 degrees from. This is the right angle, plus this missing angle, this is angle BMQ. In total, the sum of those three angles must be equal to 180 degrees according to all three. So if we found out that 90 degrees minus alpha plus 90 degrees plus the missing angle BMQ, in total must be equal to 180 degrees according to all three. 90 degrees plus 90 degrees is 180 degrees. So in total we have 180 degrees plus the missing angle BMQ minus alpha is equal to 180 degrees. We have 180 degrees from both sides of the equation, so 180 degrees will get cancelled, and we left only if the missing angle BMQ minus alpha equals to 0. Here we did alpha to the equation and we found out that the missing angle BMQ is equal to alpha degrees inside. This is the missing angle BMQ. This is the missing angle BMQ is equal to alpha degrees inside. So in the small right triangle BMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this part this angle must be equal to 90 degrees minus alpha according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two right triangles, that is to say the right big triangle APM and the right small triangle BMQ, those two right triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So I should found out that all the three angles of the big right triangle APM are correspondingly equal to all the three angles of this small right triangle BMQ. And therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side PQ of the small right triangle BMQ. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side BQ of the small right triangle BMQ. AP is 9 over MQ is the missing side, so it is it is, and it is equal to PM is also the missing side, so it is, over BQ is 4. So in total, we found out that 9 over MQ equals to PM over 4. Here, of course, multiply this equation, and we found out that 9 times 4 is 36, so 36 equals to MQ times PQ. Again, MQ times PQ equals to 36. In the next step, we define the center of this circle. This point is point O. So O is the radius that we define as R. OB is also the radius that equals to R according to our definition. In the next step, we join point O and M together by straight line. Point M is the point of tendency of tangent PQ with this circle. So point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that is equal to R. The radius OM that is equal to R, the radius OM is 1 to point M, that is the point of tendency of tangent PQ with this circle. And whenever you have a radius that is 1 to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did the construction. That is to say, from point O, that is the center of this circle, we do perpendicular on side AP. Again, from point O, we do perpendicular on AP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AP. This point is point M. When doing this construction, we get that the big quadrilateral LOMP. Inside the big quadrilateral LOMP, we have 1, 2, 3 arteries. The sum of 3 arteries is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, must be equal to 360 degrees, according to the rule that says that the sum of the areas in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral LOMP, we have 4 arteries. And according to all 5, any quadrilateral that has 4 arteries must be the rectangle and front square. So we have to the big quadrilateral LOMP is rectangle because it has 4 arteries. In the next step, we did another construction, that is to say, from point B, we draw perpendicular on the radius OM. Again, from point B, we draw perpendicular on the radius OM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and OM. This point is point S. So in the small when doing this construction, we get the small quadrilateral SBQM. Inside the small quadrilateral SBQM, we have 1, 2, 3 arteries, and therefore this fourth missing angle must be equal to 90 degrees inside, and therefore quadrilateral SBQM is rectangle because it has 4 angles. The next time we focus on this big quadrilateral LOMP. We know that the opposite sides of a rectangle are parallel to each other. Again, the opposite sides of a rectangle are parallel to each other. So in the big rectangle LOMP, side LP is parallel to the opposite side OM. But LP is part of the straight line AP. So if a part of the straight line is parallel to another straight line, then the straight line AP itself must be also parallel to another straight line OM. So in total, we found out that LP is parallel to OM. LP is parallel to OM. So the next step, I copied those 2 parallel lines and the diameter AOB in the new page, and we created all 50 in the new drawing. Those are the 2 parallel lines, AP and OM. The red line segment is the diameter AOB. So those 2 angles are defined as corresponding angles, and they are located between the parallel lines AP and OM, and therefore they must be equal to each other, their sizes, according to all 50. So if you define the size of this angle as beta, then the size of this angle must be equal to beta, because they are equal to each other, according to all 50. So if you find out that angle PAO equals to beta, this is angle PAO, the big angle PAO that equals to beta. And also found out that angle MBO is also equal to beta. This is angle MOB equals to beta. Angle MOB is also equal to beta. So this green triangle OSB, this angle equals to beta. This angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus beta, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the right triangle AO, this angle equals to beta. This angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus beta, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two right triangles can go into each other according to angle, side angle rule. So why those 2 right triangles can go into each other? First of all, those 2 angles are both equal to beta, and therefore they are equal to each other. In addition, side AO is equal to side OB. They are both the area of the circle that is equal to 1, and therefore they are equal to each other. So side AO of the right triangle AOL is equal to side OB of the right triangle OSB. And finally, those 2 angles are both equal to 90 degrees minus beta, and therefore they are equal to each other. So if we prove that those 2 right triangles can go into each other according to angle side angle rule. That is to say, if you prove that those 2 angles and the side that is included between those 2 angles, that is R, in this right triangle AO, are corresponding equal to those 2 angles and the side that is included between those 2 angles, that is R, in this right triangle OSB. And therefore, if we prove that those 2 right triangles can go into each other according to angle side angle rule. We have those 2 angles and the side that is included between those 2 angles in the right triangle AO corresponding equal to those 2 angles and the side that is included between those 2 angles in the right triangle OSB. And therefore, those two right triangles can point to each other according to any side angle rule. Then if you find out that triangle ALO can point to triangle OSB according to any side angle rule. And from the fact that those two right triangles can point to each other, we know that side LO, so the right triangle ALO is equal to side OSB. In the right triangle OSB, according to the rule, the corresponding sides of the right triangles are equal to each other. Those two triangles can point to each other, and therefore the two corresponding sides, that is to say LO and SB, must be also equal to each other in the left. So if you remember that LO equals to SB. LO equals to SB. So if you define the length of LO as X, then SB must be also equal to X because they are equal to each other. Again, if you define the length of LO as X, then SB must be also equal to X because they are equal to each other. We know that the opposite sides of a rectangle are parallel to each other. The opposite sides of a rectangle are equal to each other. So in the middle rectangle LOMP, side LO must be equal to the opposite side MP, but LO is X, therefore PM must be also equal to X. Likewise, in the small rectangle SBQM, side SB must be equal to the opposite side MQ, but SB is X, therefore the opposite side MQ must be also equal to X units in its length. We already found out that MQ times PM equals to 36. MQ is 6, MQ is X, MQ is X and PM is X. PM is also X. Yeah, MQ is X and PM is X. So in total we found out that MQ times PM is X times X, that is 36. X times X is 36, that is X times X is X squared, that is equals to 36. Here we took out of the equation and found out that X equals to 6 units in its length. So here X equals to 6 and here also X equals to 6. The next step we created Pythagoras theorem on this small right triangle MBQ. According to the Pythagoras theorem, in any right triangle the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the small right triangle MBQ, BM squared, that is the square of the hypotenuse, equals to BQ squared plus QM squared. And again, the small right triangle BMQ, BM squared, that is the square of the hypotenuse, equals to BQ squared plus MQ squared. BM is the missing side, so it is it is. So BM squared equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, it is 16. Plus MQ squared. MQ is 6, therefore MQ squared is 6 squared, it is 36. So in total we found out that BM squared equals to 16 plus 36, that is 52. So BM squared equals to 52. Here we took out of this equation and we found out that BM equals to the square root of 52 units in its length. This side BM, that equals to the square root of 52 units in its length. In the next step, we created the Pythagoras theorem on this big right triangle APM. According to the Pythagoras theorem, AM squared, that is the square of the hypotenuse, equals to AP squared plus PM squared. Okay, again, the right big triangle APM, according to the Pythagoras theorem, AM squared, that is the square of the hypotenuse, equals to AP squared plus PM squared. AM is the missing side, so it is. And it is equal to AP squared. AP is 9, therefore AP squared is 9 squared, that is equal to 1. Plus PM squared. PM is 6, therefore PM squared is 36. So in total, we should find out that AM squared equals to 81 plus 36, that is 117. So AM squared equals to 117. Here we took out of this equation and we found out that AM equals to the square root of 117 units in its length. This is slide AM, that equals to the square root of 117 units in its length. Our task is to find out the area of this green shape. The green shape is actually the green right triangle AMB. So we have to find out the area of the green right triangle A and B. Actually, we know that the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of the green right triangle A and B will be equal to the base BM times the height MA over 2. And again, the area of the green shape is actually the area of the green right triangle A and B. So, and the area of triangle A and B, the green right triangle A and B, must be equal to the base MB times the height AM over 2. We already found out that MB equals to the square root of 52 units in itself, and AM equals to the square root of 117 units in itself. And again, we already found out that MB equals to the square root of 52 units in itself, and MA equals to the square root of 117 units in itself divided by 2. And we have the algebraic identity that says that the square root of A times the square root of B equals to the square root of A times B. And therefore, the square root of 52 times the square root of 117 will be equal to the square root of 52 times 117 divided by 2. 52 times 117 is 6084 divided by 2. And the square root of 684 is 78 divided by 2. 78 over 2 is 39. So in total, if you know that the area that we are looking for in this equation, that is the area of the green shape, is equal to 39 square inside. Okay, again, the area of this green shape, that is the area that we are looking for in this equation, is equal to 39 square in its size. Okay, thank you very much.